Part 1. Antenna Engineering. Without an antenna, a wireless system cannot perform its function, so it's a very critical device in any wireless system. The primary use of the antenna is to propagate an information-carrying signal from the transmitter to the carrier from free space. And so the antenna functions as a transducer, and it basically is a reciprocal device. They can receive and process electromagnetic waves while they transmit. So in view of this dual capability of the antenna to transmit and receive, a separate device called the duplexer or diplexer is attached to the antenna to separate the outgoing, transmitted, and incoming received signals. There are two distinct regions called the far field and the near field. The far field region is basically any distance that is greater than 2 times d squared over lambda, where d is the largest dimension of the antenna and lambda is the wavelength. And in this far field region, only the transverse propagation electromagnetic field exists. Whereas in the near field, which is basically closest to the antenna, it basically contains the reactive and oscillating EM fields. So the far field distance r is basically generally a good approximation of the distance required to see only the outward propagating wave. An antenna can be considered as an impedance transformer because it converts a nominal RF system impedance, typically 50 ohms, into the free space wave impedance, which is about 377 ohms. So the definition of impedance is as follows. It's basically a measure of the total opposition to current flows in an alternating current circuit. It's basically made up of two components, the ohmic resistance and the reactance. It's usually represented in a complex notation Z equal R plus JX, where R is the ohmic resistance and X is the reactance. One can think of reactance as basically a resistance to change. Examples are charges for capacitor and magnetic fields for inductors. In general, impedance is determined by closed form solutions out of textbook. And then it can also be determined by modeling and simulation, or more realistically by measurement with a network analyzer. In this case, the antenna impedance is measured at a feed point, such as a port. The standard impedance for a coaxial system is 50 ohm, and VSWR, which stands for voltage standing wave ratio, is a measure of how close the antenna impedance is to the reference impedance, usually defined as 50 ohm. VSWR or VISWA typically requirements are less than 2 to 1. It's also measured as return loss in dB, as shown on the table on the right. VISWA is important for two reasons. If you see the pictures at the bottom, where you have a voltage source in the transmission line and the load Z sub L, the forward voltage is going to be reflected as shown by V sub R, and that is basically a reflections of the signal source. And so visual is very important in minimizing the reflections that is shown here. And so in order to have maximum power transfer, one needs to be very careful in trying to get a certain visual. The table on the right shows the relationship between visual and return loss in dB. And as you can see, the lower the visual is, the higher the return loss is. So at a voltage standing wave ratio of 2, we will typically have a return loss of 9.54 dB, or about 10 dB. And so ideally you want to have a visual less than 2, which typically resulting in a very high return loss, and thus a lot more power transfer to the load. One important aspect of antenna design is the size, weight, and power, or SWaP. SWaP is very much depending on its use, and the requirements varies accordingly. For example, satellite applications will require that the SWaP is very, very small, because solar power is the only source, and the launch weight directly translated to cost. SWaP is also extremely important for wireless handsets because battery power is very limited and the size are getting smaller and smaller. Basically, the antenna is going to be hidden inside the casing. So in this case, the size and the power requirements are extremely important. On the other hand, SWaP may be of secondary importance for fixed wireless base station, where the AC power is available, and of course the weight for the electronics is not really a major concern, although a current industry trend is moving toward green base station design, where power is the biggest concern. Virtually all antennas radiate electromagnetic wave more strongly in some directions than in others. This behavior is measured by using field patterns, which are three-dimensional vector quantities that are functions of theta and phi, which are the angle used in the standard spherical coordinate systems. So field patterns are typically displayed in 3D color plots, or in this case, shaded black and white, or by using several two-dimensional planar cuts. In the pictures to your right, which are basically the field patterns for the parameter horns and the short dipoles, the E-plane cuts are often the principal planes, which are the XZ and YZ plane, while the XY plane is known as the H-plane cut. The power patterns are usually normalized, and they're visualized also in 3Ds or in 2D planar cuts in pretty much exactly the same way as the field patterns. The power pattern and beam width of an antenna basically describe the spatial variation of the antenna response, whether it's a receive or transmit antenna, and usually it's expressed in dB. As shown in the picture on the left, the beam peaks, also known as boresight, happens at about 33 dB. And so the minus 3 dB beam width, which happens around 30 dB, constitute a 3 dB beam width of about 5 degrees. One can also talk of a side lobe level, which basically is the distance from the beam peak to the first side lobe. In this case, the side lobe level is around 27 dB. One can also talk about a null in the power patterns. In this case, this first null is located at about 7 or 8 degrees in the azimuth plane. One can also depict the power patterns in three-dimensional. And in this case, the power pattern or gain is expressed in dB and at a particular frequency such as 230 megahertz. And the colors are used to shade at the volume, the gain of the antenna at a certain positions in three-dimensional coordinate systems. Antenna directivity. The directivity D of an antenna is defined as the ratio of the radiation intensity, which is basically expressed here as the U of phi and theta. And basically that's a ratio of the radiation intensity to the radiation intensity average over a sphere. So here D is basically the normalized ratio formed by U of theta and phi over U average over the sphere. And it's also equal to S of theta and phi over S of theta and phi average, where S is the Poynting vectors defined in electromagnetic field theories. So basically directivity D of the antenna is basically a function of the angular values theta and phi, but if no direction is specified, then the direction of the maximum radiation intensity is often implied, and so the directivity in this case becomes a single values. The gain G of an antenna is less than directivity D due to ohmic and other losses. And so the gain is typically expressed as G equal K times D, where K is an efficiency factor between 0 and 1. One thing to note is that an isotropic radiator is basically a theoretical antenna that has an omnidirectional pattern and a directivity of D equal 1. This means that all the isotropic source radiates energy uniformly in all directions over a 4 pi steradian. For an antenna, the gain is basically created by focusing energy in a desirable directions away from the undesired directions. So an antenna gain has to be referenced to some standard, either by an isotropic source or by a dipole. The isotropic source is basically defined as a uniform radiator, whereas the dipole usually has a figure-8 field patterns. Gain is usually specified in decibel, or 1/10 of a bell. The bell is mostly used in telecommunication, electronics, and acoustic, and was invented by engineers from Bell Labs to quantify the reduction in audio level over 1 mile length of standard telephone cable. It was originally called the transmission unit, or TU, but it was later renamed in 1923 in honor of the laboratory founder, Alexander Graham Bell. It is noted that a dB is always a relative measure. Without knowing the reference is not very useful. So dBi is defined relative to an isotropic antenna, where dBd is defined relative to a halfway dipole antenna. So 0 dBd is equal to 2.15 dBi. On the other hand, dBq is defined relative to a quarter wave whip antenna. So 0 dBq is equal to minus 0.85 dBi. And dBic is defined relative to a circularly polarized isotropic antenna. There are a few ways to approximate gain, and for high gain antenna, most of the dishes, the gain is approximately equal to 10 log 10 of 26,000 divided by theta 1 times theta 2, and this is in dBi. In this expression, theta 1 and theta 2 are the 3 dB beamwidth in degree in principal plane. One can also approximate gain as being 10 log 10 of 4 pi effective aperture A sub e over lambda square, and we will talk about the effective aperture later. A convenient approximation for beamwidth is, this is the 3 dB beamwidth, is 70 degree times lambda over d, where lambda is the wavelength and d is the antenna diameter. These approximations are typically good for initial rough order of magnitude estimate. And note that here G and beamwidth relationships have explicit size to wavelength relationship. The effective aperture A sub e basically include the efficiency of the aperture, and is typically 55% for the dishes. Effective aperture. Basically, every antenna has an effective aperture, or A sub E, that can be viewed as an area over which the antenna effectively captures the incoming EM waves. The effective aperture generally differs from the antenna physical aperture, which basically is the cross-sectional area of the antenna physical structure. For example, the dish area. The effective aperture can be larger or smaller than the physical aperture, depending on the antenna type. If you recall, the directivity of the antenna is related to the effective aperture by the expression d equals 4 pi a sub e divided by lambda square. Therefore, more gains would require either a larger effective aperture or area, or operation at a shorter wavelength or higher frequency. The polarization of an antenna describes the orientation of the electric field vector of the radiated electromagnetic field in the antenna far field as the field propagates away from the antenna. So antenna can radiate linear, as shown here, elliptical, or circular polarizations. In linear polarization, the electric field vector oscillates along a straight line as the wave propagates outward. Examples would include antennas that are vertically polarized, horizontally polarized, or perhaps having a linear 45-degree polarizations. For circular polarization, the electric field vector rotates and traces out the locus of a circle as the radiated wave propagates. Circular polarization is further divided into left-hand circular polarization and right-hand circular polarization, depending on the sense of rotations. For elliptical polarization, the electric field vector traces out the locus of an ellipse as the radiated wave propagates. Elliptical polarization can also be given as a right-hand or left-hand sense, the same way as circular polarization. As a matter of fact, both linear and circular polarization are a special case of elliptical polarization. A measure of antenna polarization is called axial ratio, or AR, which is the ratio of the major to minor axis in the polarization ellipse, and usually expressed in dB. If AR equal to 0 dB, then it's perfectly circular, and if it's equal to infinitive dB, then it's perfectly linear. Polarization mismatch. For maximum power transfer and signal reception, the transmitter antenna must be of the same polarization and orientation as the receiver antenna. If the transmitter is vertical, linearly polarized, the receiver must also be linearly polarized and oriented vertically. So polarization mismatch is a significant concern in wireless system design, implementation, and operation. For example, a linearly polarized antenna can receive circular polarized signal but with a 3 dB loss. Also, an antenna designed for vertical polarization will not be able to receive a horizontally polarized signal. In practice, there is a very small amount of horizontally polarized signal present, and this is called the cross-polarization or cross-pole term. Other reasons for having received different polarizations include phased array rotation in satellite communication, alignment issues, and range attenuations. There is also an important parameter called antenna bandwidth, which is defined as the frequency range over which some parameter varies within a prescribed limit. So the different type of antenna bandwidth may include impedance, which basically varies according to some visual type of specification, and this is the most common. Also, it can be defined with respect to the gain, in this case is 3 dB, and also it can be defined with respect to beam width and axial ratio, which is a measure of the circular polarization, and 3 dB is usually used. An example of bandwidth with respect to visual is shown here in the figure, where the visual varies over a lower and upper frequency limits with 2:1 as the threshold for definition. And so the upper and lower frequency would define an absolute frequency range in kilohertz, megahertz, or gigahertz, or as a percentage of bandwidth, reference to some center frequency. Now let's talk about the different antenna types. They are classified in many ways. They could be classified by frequency bandwidth, whether it's narrowband, broadband, or ultra-wideband. Or they can be classified by physical designs, whether it's a reflector, an aperture antenna, a wire antenna, or a printed circuit antenna. They could also be classified by pattern characteristic, whether it's omnidirectional or very high gain antenna. They could also be classified by electrical size, where they are small or large, or by operational mode, where they are traveling wave tubes, surface wave, or guided wave. Or they can be classified by scanning characteristic, with no scanning, mechanical scanning, or electrical scanning. Examples of the wire antenna, which typically give 2 to 3 dBi of gain, are loops, dipoles, folded dipoles, rhomboid, long wire, twin wire, and helices. And the example of aperture antenna, which basically gives somewhere from 3 to less than 20 dBi, consists of reflectors, dishes, which are typically normally used in satellite communications, lenses, flat panel, and horns. The Yagi antenna, formerly named Yagi-Uda antenna, basically was invented by Dr. Yagi and his graduate student Uda. It consists of a single driven element, and one or more parasitic elements working as reflectors and directors to provide the necessary gain. The elements can be half wavelength dipoles or full wavelength loops, and that's the reason you see many elements optimized for different frequencies. The cross-dipole Yagi can be used to create circular polarizations. Most Yagi antennas give moderate gains somewhere from 6 to 20 dB and relatively narrow impedance bandwidth, typically about 2 to 5%. The Yagi antenna have common applications in VHF and UHF earth stations, or even in the wireless LAN systems. As shown here, the more elements you have on the Yagi antenna, the smaller the beamwidth is. The helical antenna has a helical radiating elements plus a reflecting ground plane, and they typically radiate end fire. The helical antenna typically have moderate gains around 10 to 20 dB depending on the axial length. It has wide impedance and gain bandwidth, typically in the 50% range. The helix circumference is approximately 1 lambda spacing between turns of about a quarter of a wavelength. The helical antenna are typically used at VHF and UHF frequency range. The quadrifilar antenna shown here is related to the helix antenna. It is also called a volute antenna. And it consists of 4 helical arms, usually about 1/2 a turn, spaced 90 degrees apart and fed 90 degrees out of phase. The antenna pattern for the quadrifilar antenna is mostly omnidirectional, as shown here, and it's circularly polarized over most of the pattern, but it has low gain, typically 2 to 6 dBIC, but it has compact size with a diameter of typically 0.2 of lambda and a height of about 0.3 of lambda. So their commonly applications are in the GPS, LEO satellite, and TT&C links, TT&C being the telemetry and command and controls. The turnstile antenna shown here is similar in performance and characteristic to quadrifilar helix. It used the cross dipole on top, fed 90 degrees out of phase to generate circular polarizations. The bottom pair of the cross dipole act as a reflectors, and effectively is a 2-element Yagi configuration. The turnstile antenna pattern and gain are similar to the quadrifilar, except that the circular polarization and the gain degrades more rapidly toward the horizons. But they are simple to construct, and they are commonly used in VHF LEO satellite. As I mentioned before, the dish antenna are the most common antenna type associated with satellite communication. So this surface has a parabolic shape, and basically the energy from the feed is reflected by the dish and focused to a tight beam. In all dish antenna, the surface smoothness and the shape is very important, and the manufacturing really is the limit here. But they have very high gain, typically from 10 to 50 dB, depending on the size, and very narrow beam width, could be a fraction of a degree. But the diameter is large compared to the wavelength, typically 10 to 1,000 times the wavelength. And that's how the dish antenna got a very, very small beam width. And so the dish antenna not only find the application in satellite communication, but also in terrestrial microwave link. The horn antenna has a waveguide feeding a flare metal horn, and the horn can be rectangular or conical. The polarization can be linear or circular, and the horn antennas typically have very wide bandwidth, basically determined by the waveguide bandwidth. The horn antenna have very well-defined patterns and gain behavior, and they find their common application in dish feeds in gain standard and array elements. This is a picture of a very large horn aperture. It's 20 feet by 20 feet, 50 feet long, built at Bell Lab in Holmdel, New Jersey, back in 1965 by Dr. Panzias and Wilsons. The patch antenna are formed by edging structure on a PCB material. These are called microstrip antenna. The back of the materials is a solid ground plane, and typically the rectangular patch dimensions are in the half wavelength in the printed circuit board. The typically impedance bandwidth are narrows from 2 to 5%, but other designs have wider bandwidth. The pattern for the patch antenna are pretty broad, pretty low gain, about 0 to 6 dBi or worse, and they find the application in the GPS receiver or elements in antenna arrays. In wideband antennas, the bandwidth are typically greater than 10% of the carrier frequency. And also by the definition of the impedance bandwidth, they could range from 2 to 1 to 10 to 1 impedance bandwidth. The geometries of these wideband antenna are defined by angles. and the gains are usually low from 0 to 12 dBi, and the beam width are usually very large. The typical type of wideband antennas are locked periodic dipole array, the spiral array, the conical spiral, or the sinuous antenna. An area of importance is phase array antennas. And typically, it's an array consists of two or more antenna elements located and fed such that the field act in a certain direction and cancel in others. The elements of the phase array can be any type of antenna, from patches, as shown here, to very big dishes like in the astronomy applications. The spacing of the antennas and the electrical phasing and amplitude for the individual element feed is critical to the array performance. Example shown here of the Cobra Dane anti-missile radar. And this is a phase array that is used for the Inmarsat commercial satellite. As mentioned before, by changing the phasing between the antenna elements, the array beam can be steered and or shaped according to some specifications. They will result in multiple beams and rapid beam steering in terms of milliseconds to switch from one beam to another. And for that, there's an anti-jam capability by creating the pattern nulls towards a jammer. This is an example of the multi-beam antenna, or MBA, in the Defense Satellite Communication System. In phase array terminology, a beamformer refers to the phase shifter, the combiner, and the attenuator or amplifiers. That are behind the actual antenna. This is an example of a dual channel beamformer that can form two beams independent of each other. So by replicating the phase shifter and the power combiner, one can create another channel for the beamformer to form a separate beams. The smart antenna refer to the incorporation of the beam steer phase array and the use of signal processing techniques to shape the beam patterns according to some optimum criteria. Either it is to create a null in the antenna patterns in direction of an interfering source, or to provide additional gain in the direction of the signals of interest. Smart antennae are also called digital beamformers or adaptive array due to the use of the statistical signal processing algorithm. Smart antenna can also be used to increase the capacity of wireless communication networks through a technique called Space Division Multiple Access, or SDMA. Some of the well-known basic signal processing algorithms that are used in smart antennas are the least mean square, the sample matrix inversions, the recursive least square, conjugate gradient method, constant modulus algorithm, and the least square constant modulus algorithm. Antenna designs and measurements. The engineers typically start out with requirements, and these requirements are often iterative, meaning they will need to be repeated several times in order to get to where we want to go. The popular design approach is to use commercial electromagnetic software to design and analyze the antenna performance. And some of the commercial EM software are based on the methods such as finite element method, or FEM, finite difference time domain method, or FDTE, the method of moments, or MOM, and physical optics. However, measurements are generally viewed as the right answer to validate the computer analysis, and one can resort to outdoor open area test site, or OATS, or an indoor compact range and anechoic chambers. So the typical setup for the OAT, or a indoor anechoic chamber, has a transmitting antenna and an antenna under test, typically located directly across the transmitting antenna. It may also contain a positioner to scan the antenna under test in azimuth and/or elevation, and/or to change the orientation for the cross-pole measurements. In both the planning and operational phase of deploying an indoor or outdoor wireless network, RF site survey must be performed to optimize network performance and to reduce implementation, operating, and maintenance costs. So indoor survey typically involves walking around the facility and measuring the signal strength either from a wireless network access point or from potential source of interference, or from both. In this case, we will use a signal strength meter or a laptop specialized in RF signal mapping software, or a more sophisticated setup with a GPS location recorder and a spectrum analyzer. On the other hand, outdoor surveys for wireless cellular network are done in much the same way as indoor surveys, but they deal instead with terrain maps rather than building plans. Signal strength measurements are done with RF drive surveys in a vehicle outfitted with antennas and measurement equipment. Software planning and analysis tool also exists for cellular network to analyze multipath propagation and signal strength for a particular coverage area. Much of the measurement equipment is similar to that for indoor networks, though they are more specialized. The basic measurement procedures are also similar. They identify sources of interference, record signal strength at various locations, and then optimize the network coverage and performance. Site survey must also be done periodically as part of an ongoing network operations plan. Base stations primarily use two types of antenna, omnidirectional and directional or sector antenna. Omnidirectional antenna are typically used in rural areas or at lower capacity sites where sectoring is not required. Most urban and suburban cellular base stations are sector antenna that must meet large capacity demands, with the 120 degree sector generally the most popular. Most base station antenna are mounted on standalone towers, but could sometimes be mounted on other man-made or even natural structure. In this example, two GSM base station antennas are disguised as trees in Dublin, Ireland. Base station antennas are usually designed with moderate gains of anywhere from about 5 dBi to 24 dBi and typically specified in dBd. They are often designed with linear polarization and slightly down-tilted, but could have dual polarized antenna with plus or minus 45 degree polarization to take advantage of the polarization diversity combining scheme. The antenna down tilt is a well-known technique used to optimize the radio network. It helped to reduce the path loss, the delay spread, and the transmitted power and system interference. The down tilt could also strengthen signal from the home cell and reduce co-channel interference, thus increasing system capacity and improving network performance. Early network deployment used a static tilt model where the tilt angle was preset and optimized during the initial network operation. Any further change in the tilt angle require a costly site visit by tower crews to reposition the antenna. More recent development have focused on dynamic antenna tilt control, where modules that can be controlled from operational center via internet or secure channel. So further network optimization can be performed. For example, different tilt angle could be used at different time of day to accommodate the varying traffic loads. Indoor antenna are omnidirectional or directional and used in such device as access point and wireless routers for wireless local area network. Omnidirectional antenna provide the widest coverage and allow the system to be designed with circular overlapping cells from multiple access points throughout the buildings. Omnidirectional antennas generally have low gains of up to about 6 dB, but using higher gain omnis can reduce the number of access points required, thus reducing the system costs. The higher gain antenna, typically from 6 dBi to 20 dBi, can be used to cover large and narrow areas or in short link between buildings. Directional antenna can also reduce the number of access points required in some applications. Manufacturers are continually developing new antenna with diversity to help solve building coverage issue in wireless LAN applications. The mobile handsets antenna have complicated design due to the severe size constraint and overall system issues. They typically have low gains and omnidirectional coverage and have to be small, so these antennas are inefficient radiators. In early design, a retractable monopole is a good, but really not a preferable choice for handset antenna. But more recent popular design are based on normal mode helical antenna that can be easily printed on dielectric film and roll into a round shape with the dielectric to cover to form a short antenna stub for handset. Here's an example of the helical antenna with the helix and the reflectors and the coax that used for feeding the RF electronics, shown here as an example. Another type of mobile handset antenna is the planar inverted F antenna, which is another good design to be enclosed in a handset. It's really a combination of the wire and patch antenna structure and can also be designed for dual or tri-band use in global roaming handset. A simple half wavelength patch antenna is shown here with the radiation pattern, which is quite omnidirectional at 900 megahertz. More recently, multiple input, multiple output, or MIMO techniques have been applied that place multiple antenna at the retransmitter and receiver to improve wireless system capacity and performance. The basic idea behind MIMO is to exploit the space resource for the propagation channel and combine it with sophisticated signal processing to achieve significant gain in spectral efficiency. A conventional radio link uses single input, single output, or SISO, and is subject to fading. A single output single input multiple output or SIMO channel offer diversity option at the receiver, such as space diversity and multiple antenna. A multiple input single output or MISO channel offers diversity option at the transmitter, such as pattern or angle diversity. For example, a transmit phase array antenna can steer the main beam toward a particular receiver. Also, beamforming techniques, as covered before, can be employed at the transmitter to generate multiple beams. And finally, for improved data rates, a MIMO channel allowed multiple data streams to be transmitted and recombined at multiple receive antenna. So true MIMO technique aims at system capacity improvement with the right number of receiver channels. So the fallback position is that in case where not all the receiver can handle or can have multiple antenna, the identical data stream are sent for transmit diversity or MISO. In multi-user MIMO or MU MIMO, one can handle multiple users as spatially distributed transmission resource at the cost of somewhat more expensive signal processing. So the MIMO broadcast channels for downlink, the transmitter has to know the channel's state information at the transmitter, or CSIT. It will also need interference-aware precoding and SDMA-based downlink user scheduling. In the uplink case, MIMO multiple access channel or MIMO MAC will need the multiple sender to send to single receiver wireless network. In this case, the receiver needs to know the channel state information at the receiver. This is the end of part 1.